months ago, Mark Helen and I had a discussion sort of over blogs. And so we concluded that a Zipfian distribution would be a better match for measuring, trying to predict the kind of performance that we would get from running real data than a uniform random distribution for indexes. So iibench is this benchmark that I talked about last year. It's a benchmark that inserts data into a database. There is a primary key, which is an auto-increment key, so that's easy to deal with. It's got 3 indexes, which are essentially random. And as you get out to 1 billion rows, it becomes a problem when you have only over a couple gigabytes of RAM because it doesn't fit anymore, and disk head starts moving slowly. And so Mark, like that, he converted it from the C++ code that we had to Python, and that's the state of the art. So we discovered, basically this dialogue that we needed to have a different distribution than uniform random distribution, because the world isn't uniformly random. Some things occur much more often than others. So a Zipfian distribution is one that, for example, models the frequency of words in a natural language. It says that the second word occurs half as often as the first word, and the third word occurs 1/3 as often as the first word, and the ith word in general occurs 1/i times as often as the most frequent word. So that's a Zipfian distribution. So we went and modified, here's the class, we modified iibench to implement Zipfian distribution. So I thought I'd spend a moment sort of showing you how this works. Here's the code that actually finds the code. And what we did is we made a big array full of numbers that exhibit a Zipfian distribution. And then we fetch a random one of those. So that's what this code does, is it basically grabs a random number and then looks up in this cache, which is just an array, random value. And to fill in that number, basically we had to create an array. And what we did is we filled in a bunch of values, and the number of items we filled in, well, when I was 1, we filled in a certain number of those values. The cardinality might be 1,000,000 or something, so we filled in 1,000,000 ones. And when I was 2, we filled in 500,000 of the second thing, and 1/3 of a million of the third thing, and so forth. And thereby build up this big array, which for the interesting data sizes that we're talking about, it turns out that the Zipfian distribution, when you actually make that array, is sort of, for interesting data sizes, is about 10 times bigger than the actual array. So if you say I want a Zipfian distribution where there's 1 million distinct values that are going to appear, you need an array of about 10 million in order to make that happen. And we did all this in order to make this code run really fast because we were finding that it was running too slow. So we went and made that work, and it's great. And then we measured it, and so here's the performance difference. This is NODB. In green is the uniform distribution, and in red is the Zipfian distribution, which, if anything's worse, so I can't explain what's wrong with that. And it's basically indistinguishable. So the experiment, I don't know whether it's a failure or what, but it hasn't done what I want. And the performance for the Tokatech database is still faster, and it's essentially indistinguishable from the previous one. I don't know whether that's one data line or 2. So
you haven't gone far enough in your asymptotics. Put a 10 billion rows in there and maybe.
Well, you can get iibench off the web and you can try it. It's a launchpad.
Naturally dead in there.
I would really like to know what I'm doing wrong that's not making this, because Mark and I thought it was going to be like 10 times better. Is that Mark?
Not careful.
Does that sound right? We thought it would be like 10 times less disk misses or something.
How did you insert the data? It also depends on which order. If you still need to insert them in random order, I mean 1, 2, 3, and then you do all the ones and everything else, you still get quite a lot of 6. And if you would first insert all ones, 2s and 3s, then you would get totally different.
Well, we're inserting them in they're random. It's a Zipfian. It's randomly chosen numbers with a Zipfian distribution, so it's not going to be in order, because that's not what happens when you trickle load data.
That's the thing with you look at real data. Usually you get data from a region like zip codes. So you get everything in one year data.
Well, that's not a hard problem to index if the data's coming in a sorted
But
order.
usually you get them in clumps.
Well,
Monty, but our whole discussion on Zipfian came out of a block trace that I took from NODB, where I was actually looking at the pattern of accesses to blocks. And I fit the curve, and I said, hey, I don't understand this, who can explain it to me? Looking for free help. And Bradley took the bait and explained
That
the
is not
distribution.
explainable.
This was for a production server, so hundreds of tables over 24 hours. I got all block accesses, and then I looked at the miss rate as a function of cache size. And with that result, miss rate as a function of cache size was fed by Zipfian.
so there's some things I don't think we completely understand about this, but we're making some progress.
Thank you, Bradley.
So thanks.